All right. Thank you very much, Hans. Thanks all for coming. As promised, I will teach you how to manually convert binary floating point numbers to strings. But before I start with that, why is this even important, or why is this interesting? So this is some JavaScript code, and if this, JavaScript is special in that its number type is the floating point type. So these are actually all floating point constants, floating point operations. And now if this ends up in the inner loop of your program, which part do you think is going to, dominate the runtime of your program? Well, it's going to be the float to string conversion, which is pretty darn slow right now. And I hope that I can convince you it doesn't have to be that slow. But there is also another angle to this work, which I want to talk about. And in order to do that, I have to go back in time. Back to 2003, when I left Stanford with a master's in computer science. And there were all sorts of things that I could start to do. And of all the things that I could do, I decided to write my own Java VM. Which, I hear in this group is perfectly normal. So that's good. And I have to say, writing a simple Java VM that can run Hello World is actually pretty straightforward. And so over the next months and years, I made a bunch of progress. I added a lot of functionality to it. And it turns out you can do a lot in Java without ever touching floating point numbers. But at some point, you get to this example where someone writes Hello World with a println of 0.3. And so, my studies had prepared me very well for writing a Java VM. All of the low-level functionality is pretty straightforward. But when I came to Java lang double toString, I didn't even know where to start. I was looking at it and I said, I have no idea. Let's look at an existing implementation. All right. And so, unfortunately, I can't exactly retrace my steps back then. I believe that I looked at the source code of some Java VM from IBM, I think. And so I looked at the code. And in order to generate these strings, it had like 10,000 lines of code. I mean, what? 10,000 lines? That can't possibly be the right way to convert floating point numbers to strings. And so, I started to look at the problem. And let's look at an example. So this is a 16-bit floating point number. The format is pretty simple. There is a sign bit, there is an exponent, there is a mantissa. The formula to compute the actual exact value is pretty simple. You take the sign bit. If it's 1, then it's a negative number. Then you take the mantissa. There is a little thing that you need to be careful with, which is that there is an implicit 1, which isn't actually stored, but you have to sort of add back in. And then you take the exponent, and it's biased. So you subtract the bias, and you get your number. So, when you do this, you just copy the parts into the right places in the formula, which is really straightforward. And you get 1,229 times. All right, so there is one thing I did here, which is I moved the decimal point all the way to the right, so that this is actually, what is 1.001? I don't know. But we can easily make this an integer number. So we just move it all the way to the right, and then we get 1,229 divided by 4,096, and that is exactly 0.3000488282125. Wait, I wanted to print 0.3. I didn't want to print, this number. So what's going on here? Let me clean this up a little bit. So this is the exact value. Now, if we look at the number line, what's the next larger number? What's the next smaller number? And these are also, these kind of longish numbers. And what you can see here is that every binary floating point number has an exact decimal equivalent. But not every decimal number has an exact binary equivalent. And the reason for that is that, powers of 2 and powers of 10 are only compatible in one direction, not in the other. Now, why do we get this number instead of 0.3? Is this the closest number to 0.3? And the way we can see that is by adding these midpoints. These are halfway between the floating point numbers. And again, these are fairly long numbers. But the idea is 0.3 lies in exactly this this area that is marked here. And so the number here is actually the closest number to 0.3 that we can have in a 16-bit floating point number. All right, so let's get back to the original topic. There is this awesome paper from Guy Steele and John White, which was published at PLDI 1990. And they looked at this problem, and they came up with 4 rules about how to print floating point numbers. And the first rule is the algorithm has to preserve information. So if you print a number and then you read it back in, you want to get back the original number, right? Exactly, if possible. Now there are, some cases like NANDs where we drop some information, but ignoring that, for the most part, we want to get the exact number back. And if you have that, then the second criteria is you want to print the shortest number that you can that still maintains this first criteria. And then there may actually be 2 options, right? There may be, or more than 2 actually. There may be, a priori, there may be up to 10 possible values. The last digit may be somewhere between 0 and 9. Now, of those numbers, you want to print the one that's correctly rounded. And what does correctly rounded mean? Well, we usually assume round even. All right, so that's great. So let's go back to our example. Let me clean this up a little bit. Let me turn this line 90 degrees so that we can more easily see what's going on. So this range, this is the range between the halfway points. This range is the range of numbers that we're allowed to print by the first criteria. So by starting with this range, we already have the first criteria hard-coded into the design of the routine. But what about minimum lengths and what about correct rounding? So for minimum lengths, well, how about we just start cutting off digits at the end? Let's do that. Let's cut off a couple of digits and another and a few more. Now, can we keep cutting off digits at this point? Now, if we do, then the middle number, the exact number, looks like the upper bound. And so we need to be careful in this case. And unfortunately, I can't explain how exactly to do that. It's all in the paper. But what you need to do is you basically need to keep track of were there any non-zero digits in the upper bound? And if yes, then sure, it's fine. And the same is true for the lower bound, actually. So if there were, the lower bound is a little bit different, but if there were any non-zero digits in the lower bound, then you cannot have the middle value go to the lower value. You have to round up. And so this gives you very simple rules for what you need to do. And so you cut off a couple more digits, and you end up with 0.3. And this is actually the number that you should print for this 16-bit floating point output. That leaves correct rounding out. And again, there is actually a fairly simple rule here, which is you look at the last digit that you cut off. If it's above 5, you need to round up. If it's below 5, you need to round down. If it's exactly 5, and if the remaining digits are all zeros, then you have to round even. So that's it. Correct rounding, all achieved. This is simple. This is correct. If you ever have to implement float to string conversion, this is the first thing you should do. Implement a simple, correct algorithm that gives you the right output. And so I did that. I've never seen this algorithm described anywhere, but it seems odd that no one has because it's so simple and straightforward, and you can implement it in less than 100 lines of code. Assuming that you have arbitrary precision library available, which of course I didn't count in the 100 lines. All right, so that's the easy part. Now, how can we make this fast? Well, why is it slow in the first place? I said arbitrary precision arithmetic, but where does it come from? All right, so I'm going to look at 2 steps here. The first one is I'm going to change these computations to only use integer operations. And then when I cut off digits, I want to cut off as many as possible. And I hope that I will be able to convince you that I can do this correctly, although there is one piece that I will have to defer to the paper because it's pretty complicated. Let's go back to the exact value computation. Now, we want to make this integer operations. So we move the decimal dot all the way to the right. So we have to subtract the length of the mantissa from the exponent. It's easy so far. Now, this number, I call this E2 in my paper. I apologize for the bad naming. If E2 is a positive number, then we have an integer. We're done. Great. If this is a negative number, then we multiply this by 5 to the power of E2 times 5 to the power of minus E2. So what happens here? Let's look at the example again. Let me clean this up a little bit. So the main computations we had was 1,229 times 2 to the power of minus 10 times 2 to the power of minus 2. And E2 in this case is minus 12. So that's exactly the case we wanted to talk about. So we multiply by 5 to the power of 12 times 5 to the power of minus 12. And now 5 to the power of minus 12 and 2 to the power of minus 12 combine into a nice decimal base. So we only have to compute 1,229 times 5 to the power of 12, and we get exactly this number here. And this is not coincidence, right? This is the exact number that you need to print. And now you have a decimal exponent. You can convert this to a string. You can add the decimal dot in the right place, and you're done. So if you ever need to do this, this is how you do it. This is, so we got integer operations. Now we want to skip digits. So let's look at the example again. We turn this into integers. So, we actually drop the O point at the beginning, and we need to keep track of the decimal exponent. Let's assume that we do that somewhere on the side. And let's focus on just the number itself. We have to do it for all three values, but I'll skip that here in the interest of brevity. So this is, again, the same as before, and now we want to remove digits, so we divide this by 10 to the power of, say, 8. Remove 8 digits. Now this is going from the example to the general case. This is actually the general case. All the cases look like this. This is true for all numbers that have a negative exponent E2. The numbers that have a positive exponent, it looks different, but the approach is basically the same. So now we have a power of 5 and a power of 10 here. Now these cancel out, and it so happens, this is a little bit tricky. How many digits can we actually cut off? And I have a formula in the paper about exactly how many we can cut off. And by that formula, it turns out that the number of digits we can cut off is always smaller than the exponent minus E2. And that means these 5s all cancel out. Great. So why is this a problem? Why is this difficult to compute? Now, the input is, approximately an n-bit integer if you have an n-bit floating point type. And the output is an n-bit integer. See the paper for proof. But this power here is pretty large. Even after canceling it out, especially as you get larger floating point types, the range of these numbers gets very large. Let's look at double, for example. Double has 64-bit, so the input, V is 64-bit integer, the output is a 64-bit integer, but this multiplier there is an up to 750-bit integer. And that's causing all of our trouble. So let's think of this as a binary longhand multiplication. You all know longhand multiplication, right? Okay. So we have a number v, which consists of some number of bits, and we have a factor p, which consists of some number of bits, and then we get a large output, y, and then we divide by 2 to the power of q, and so what we do is we drop q bits of the output. We only need the top, 64 bits in this case. So maybe maybe we can split this multiplication into two multiplications. Oh, sorry. One more slide. There, what I just said. Maybe we can split this into two multiplications and take the topmost bits of P and the bottommost bits of P and do two separate multiplications and then add them together. And then we get two numbers and we add them and we get our correct output. Now, there is this gap here where we have a couple of bits. And if any of those bits are 0, then adding the second number does not change our output at all. And now I have looked up books and I've looked up math, formulas, and I've looked up at the internet, and I have not found a way to prove that there is at least one 0 digit in this gap. And so I had to come up with a proof myself, which turned out to be fairly complicated, and took me 4.5 pages of the paper. So if you're ever bored at night, and you want to get to sleep, feel free. If you find a better proof, I would very much like to hear about it. If there is some result from number theory that we can apply here, it would be so awesome. It turns out, so as I said, there is, under a lot of useful conditions, there is a gap here, and I can show that there is at least one 0 digit, so I can completely drop the second multiplication and only do the first multiplication. And it turns out for all the floating point number types up to 256 bits at least, we only need about twice as many bits of P as we have in our floating point type. So, the overall algorithm looks like this. I take the floating point number, I take out the parts, I take it apart, I get the mantissa, the exponent, the sign bit, I compute the upper and lower bounds. This is all really straightforward. Then I do 3 multiplications. Then I have the topmost digits, and then I look whether I can still cut off some more, cut off 2, 3 more, and we're done. And that's what I print. And these are the results. Because the algorithm is so simple, I was able to spend a significant amount of time on fine-tuning, the small operations, the things that happen between the large parts. And I started with code that was about 2 times faster than the previous best implementation, which is Grisou, or Grisou 3. And then I took that and made it, another almost factor of 2 faster, just by tuning the fine little bits. Because there is so little code in this algorithm, I was easily able to do that. Now, this is a C implementation. What about other languages? This is actually OpenJDK is orange, and there is another algorithm by a guy called Jaffer. That's the green dots. As you can see, the OpenJDK right now at head is not very good. I actually found, as part of the work, I found a number of bugs in the OpenJDK where it prints too many digits, so it's not exactly following the spec, although it's almost following the spec. So yeah, I would like to thank especially my wife, Sarah, who reviewed a lot of the early drafts, and without whom the paper would have sucked and would not have been accepted, for sure. And I'd also like to thank my friends, Christian and Tobias, who reviewed earlier drafts. So that's it. Thank you very much, and feel free to ask questions.
Steve Egdahl, University of Portland. If I had a burning desire to be able to print floating point numbers in base 13, how much of this would apply?
That's a good question. I don't know. I think base 13...
Or pick your base. Not a power of 2.
Right. So I don't know yet, right? I have to follow up on this, and hopefully I can transfer some of this to other bases. I think if you have base 6 or base 12, a lot of this work would apply, and you could basically take all of it and then basically rerun. So unfortunately, part of the proof involves running an algorithm that does that covers a fairly large range of possible input values to make sure that the number of bits work out. I couldn't find anything faster than that, and so you'd have to adjust that to go with power of 3 or power of 6 or something. But yeah.
Your timing results use C code or Java code or both?
Yes, so the first slide I showed was a C implementation against Grisou 3, which is also a C implementation. And the second slide is a Java implementation compared against other Java implementations. You can see from the slides that the Java implementation is actually significantly slower than the C implementation. I believe there's 3 reasons for that. One is the lack of large multiplications in Java. In C, I actually use the 128-bit integer type that's available in Clang and GCC, and that actually has machine support, at least on Intel machines. Whereas in Java, I have to reduce everything to 32-bit multiplication, so I can use the normal 64-bit type. So that's one of the reasons. The second one is the Java implementation always allocates memory, and then allocates even more memory and makes a copy. Because the Java string constructor has to be defensive, and so I can't just pass it an array and have it use it, but it has to make a copy internally. And the third is that as far as I can tell, the optimizing compiler is just not quite as good as the one in Clang and GCC. And I actually looked at the generated machine code by these compilers, and it's really, really good. I made changes to the code, and I saw no difference in the generated machine code because the compiler completely understood what I wanted to say and mapped it to the best possible sequence. So
I wonder if you could show your graphs again.
The one Java?
Yeah, the one
the
before.
one?
So am I correct that you've tried a whole load of numbers and you're
Right.
timing how long it took to convert each number to?
Yes.
Sure.
So the
And-
x-axis is the entire range of 64-bit floating point numbers.
Yep.
And the y-axis is the time for a single number.
So I was curious then, what is special about that number? There's one blue plus that's way up in the sky.
I think that's very likely measurement error.
Okay.
I ran this on my laptop as I was preparing the talk, and I didn't completely control all all the possible variants.
So this isn't from, do you have,
This is
did you do this in the paper, this experiment?
I controlled more variables in the data that's in the paper, so that should show nicer data. There is still some outliers that I can't completely
I guess my more
explain.
general question is, I mean, I enjoyed the talk, but I can't confess I followed all the details. Like, are there certain numbers for which there is going to be a whole lot more computation to be done because working out which digits to cut off just takes longer or something?
So,
As in, is the algorithm input dependent in terms of its runtime?
yes,
To what
yes,
extent?
it is a little bit input dependent. The majority of the code is just straight line code. There are a couple of ifs and whatnot, but there are a couple of loops as well. So if you actually have a number like 0.3, the first number it computes is 3, 0, 0, 4, 5, 6, and so on, and then it cuts off the remaining digits. So there is a loop there. So there is some input dependence though, yes. And that can't easily be seen. I could probably construct some examples to make that clearer, and get some more data from that.
Any other questions? Thanks very much.